In this chapter, we would like to continue the definition of the superstructure based upon an axis. The definition of an axis can be found on the System dialog or the System tab, and here by right-clicking on the axis, we have three main options to create a new axis. We can import an axis from an already existing SOFiSTiK database from a .cdb file, or we can simply create an axis from a 3D AutoCAD curve, or as the third option, we can create a new axis based upon placements value, and this is what I'm going to suggest you to do so, and this is what I'm going to introduce. So please click on the new axis. The first input we need to add is the name of the axis. Here we can enter maximum 4 characters. So I will add the name axis and then click OK. Now a new dialog box called Horizontal Alignment appeared on my screen. And I have an overview of the default setting, which is a line axis, so a straight line axis with a length of 30 meters. It is represented in this view area. I will make the window a little bit bigger. And now I would like to show you how to move the line here. So basically the axis can be moved with the middle mouse button. And you can also zoom in and zoom out this view by scrolling your middle mouse button. In the middle of the window, you can see the origin point of the axis, which is this point actually. And as you can see, by default, it is inserted into the 0, 0 point of the global coordinate system. I suggest you to keep with this value, and I do not suggest you to enter the real position of the axis from the road maps, because it could lead some trouble in the software. So I'm not suggesting here to add 7,000 meter and here 50,000 meter whatsoever, because the structure will be so far away from the origin point of the global coordinate system that it could lead some problems. In the next two entry field, you can add the starting tangent of this axis. By default, it is a straight axis and starting with a horizontal tangent. But if I add, for example, starting tangent to be equal with 1 and 1, then you will see that right away the starting tangent changed to 45 degrees. Of course, it is also possible to enter an angle here. So for example, instead of 45, I can add 15 and click outside, then the start tangent will be changed. Now we can set it back to 0 to have a straight axis. Then what we can do is to add different kind of segments and build up our axis with these segments. By default, the kind is set to line, but if I drop down the list, you can see that we have many options here. For example, we can define an arc, a clotoid, a BLOS, a sinus, or a cosinus segment of the axis. For example, if I choose an arc and the length to be equal with 30 meter and the radius equal with 60 meter, for example, then you will see that I received a right circle. And if I enter a negative value here, then you will see that the arc is turning to the left. So positive value to the right and negative value to the left. And of course, you also have the possibility to insert a new line after or before a certain segment. So for example, now if I choose insert a segment below the selection, then I will receive another arc right after the previously defined one. And for example, now if I change it to a clotoid, then I can say, for example, that the end radius to be equal with 60 meter. And as you can see, now I have an arc at the very beginning, then a clotoid from a starting radius of -60 to an end radius of +60. And again, if I add a new line, and then at the end, for example, I am going to choose a straight line, then I have my axis defined, for example. And I wanted to point out that the chainage values are very nicely shown in the preview. For example, at the beginning we have the chainage 0.0, then at the end of the arc we have the chainage 30.0. Then after the clotoid we are at chainage 60. Then at the end we are at chainage 90. For our particular example file, we just want to have a straight line with a length of 70 meter. So now I just need to delete the unwanted lines. You can do that by simply selecting the line that you want to delete and then click on the Delete Selected button. Also, I would like to delete the arc, so I select it and delete it. So as I mentioned, our bridge is roughly 55 meter. So if I set the length of the axis to be equal with 70 meter, then I have plenty space at the beginning and at the end of my bridge to be suited for this axis. So if I'm satisfied with the definition of my axis, then I simply click on the OK button and the axis will appear in the screen. After double clicking on my middle mouse button, the zoom extend command was triggered, and now I can see my axis from the beginning until the end in my screen. Also, I can verify that my definition was successful because below the axis I can see my newly created axis with its different properties, for example, the horizontal alignment, vertical alignment, placements, variables, and secondary axis. These are the parameters that I would like to go through together with you. If I double click on the horizontal alignment, I am directed back to the previously used dialog box, so I don't want to change anything here. But if I go and open up the vertical alignment, I can set up the vertical alignment of the axis as follows. I'm going to make the dialog box a little bit bigger again, and I will add one additional station value between station 0 and 70. And then, for example, I'm going to choose the height in the middle of the axis to be equal with 10 meter. And as you can see, here the elevation of the axis is 0. Also at the endpoint is 0, but in between the elevation changed to 10 meter. If I want, I can round off this elevation, for example, with a 100 meter radius. And as you can see, now it is really rounded. If I click OK and go to the front view, then you can see really my axis has been changed and it is following the given vertical alignment. If I now added a new structural line reference to this axis, really the structural line would follow the exact shape of the vertical alignment. However, in this example file, we don't want to do that, so I'm going back to the vertical alignment dialog box, select the middle line and delete it. Then I will click OK and continue with the next parameter. So the next parameter of the axis I would like to explain is the placements. Let's double click on it. Now you will find yourself in the placements dialog box where you can set the placements along the axis. A placement is important to set up or to create along the axis where the superstructure has something special. I mean, for example, the superstructure starts, the superstructure ends, or you have supports along your superstructure. Technically, in the background, what is going to happen is that the software is going to create a structural point at a placement, and later on, after the meshing procedure, a finite element node will be created at these placements. The placements definition is also very important when you have tendons in your superstructure, because the software tries to recognize where the superstructure starts and ends, and where you have the internal supports. Based upon this information, an automatic geometry of the tendons in the superstructure will be offered for you. As you can see, now by default we have two placements created automatically by the software. The first one is with ID P1 at station value 0.0 and the type is a support. Let's change it to 10 meters, so the starting station of my superstructure will be at 10, and the type will be, instead of support, is access at the starting point. Now let's have an overview about the stations of our superstructure with the help of one of my slides. So here is our exercise file from the front view, and as you can see, I have noticed the station values of this superstructure. At station 10, we have the starting point of our bridge or access at the start. Then at station 1070, we have our first support line. At station 37.30, we have the second support line. At station 63.9, we have our last support line. And finally, at station 46.6, we have the access at the end. Let's create the very same stations in the placements definition dialog box. Okay, so at P2, we need to enter 10.7 meter, and it's going to be a real support. Now I would like to create a new entry in the placements dialog box, so I will simply select the very last line and then click on the button which says Insert Below Selection. By default, the type has been copied over, so from a support, a new support type will be created. Only the station value is what I need to overwrite. Let's do so and add it 37.30 meter and then click outside. In this way, the offset from P2 to P3 was done with an automatic offset, but if I know the span length, I can also add this value in the station offset. For example, in our case, the span length is 26.6 meter. And now if I select the last line and enter a new line below, then the support type of placement will be copied over with a station offset of 26.6 meter. Now I would like to create the access at the end of my superstructure. So I will select the first line, access at start. I will add to the station offset the total length of the bridge, which is 54.6 meter. And then I will click on the Insert Below Selection button. And as you can see, now I have received 64.6 meter access at the start, and now I just need to change it to access at the end. Okay, so now we are done with the definition of the placements. We do not have the structure, the superstructure yet, but these placements are very important for us because we are going to define the structural lines in between these placements. So it means that at the beginning and at the end of our axis there will be no any structural lines defined, only between the placements. The definition of the placement is also very important if we want to parameterize our cross-section. For example, in this example file, we would like to set up a non-effective area in the cross-section that is changing along the axis. Let me show you the final model, what I mean by that. This is how the final model will look like. If we have a closer look and zoom in, with the grayed area, you can see the non-effective area of the cross-section. We would like to create this non-effective area because of the shear lag effects. A part of the cross-section is not working fully. So basically, what we would like to achieve is that from the center point of the cross-section, 2.3 meter of the cross-section is working fully, and the rest 0.7 meter is not working. However, the length of this non-effective area or non-effective length is changing. From the middle support in the direction of the longitudinal axis in 4 meter distance, this effect should be fade out. How can we achieve this? Basically, we need to set up a variable, and the value of the variable is 2.3 meter above the support, and the value of the variable is changing along the axis. Over the middle support, its value is 2.3 meter, and 4 meter away from the support, the value of this variable is 3 meter, which is the half width of the cross-section. In order to control the value of the variable, we need to set up new stations. The first station needs to be created where the variable value is 3 meter. The next station needs to be created where the variable value is 3 meter for the first time. Another station value needs to be created where the variable value starts to decrease once more. And finally, we need to make a new station at the end of the change of the variable. So to summarize, you need to create stations, not just the end at the end of the superstructure and at the supports, but also if you have or want to have a parameterized cross-section and you want to control the value of the variable along the axis. Now let's go back to the definition of the placements and add these new placements to our axis. To be able to do so, I will give you some dimensions for easier creation. So the change of the variable that controls the non-effective area starts 4 meter away from the support line, and on 1.5 meter it develops its maximum value. So the way how we can define this is if we select the middle support, and for the station offset we enter 4.0 meter and click on the icon that insert a new line above our selection. If we do so, a new station has been inserted really 4 meter before our middle support. What I would like you to do is to go to the ID field and rewrite the name to N1. With the ID starting with N, I would like to refer to the non-effective variable. Also, we need to change the type of this placement. Instead of support, please choose from the drop-down list the none. Because it is not an access at the start or at the end, nor a support, it is simply for the definition of a variable. Now I would like to change the station offset to 1.5 meter and simply click on the insert line below the selection. And now really 1.5 meter away from the first N1 station, a new station has been created with the same type. The only thing I need to overwrite is the ID, which should be N2. Now I would like you to change the station offset value to 1.5 meter and simply click on the Insert below the Selection button. And as you can see, really, with 1.5 meter, a new station has been created with the same type, none. The only thing I need to overwrite is the ID of this new station, which should be N2. Okay, now I would like you to select again P3, which is the middle support, and change the station offset to 4 meter again, 4.0, and click on the Insert below the Selection button. Now I need to change two things. First, the type of the placements to be equal with none, and also the name or the ID to be N4. Now if we select the line and add the station value of 1.5 meter and click on the Insert above the Selection button, then a new station will be created with 1.5 meter offset and the type none. And again, the only thing we need to change is the ID number, which should be N3. Now if I make my dialog box a little bit bigger and moving this middle line, then you will see all the placements that should be defined in your model file as well. So now we have a station access at the start, then the first support line, then come two station just because of the definition of the non-effective variable, then comes the middle support, then again two station values for the variable of the non-effective area again. Then we have finally the last support and the access at the end. Before I click on the OK button, I would like to explain something and show you something in this placements dialog box. And it is the following. It is also possible to make a multi-selection in this dialog box if you select more lines with the help of the control button of your keyboard. Then a general box or dialog window will appear on the right side. Let's make the window a little bit bigger. And if you want to change, for example, the type of the selected placements from none to construction point joint, you just select it from the drop-down list, and as you can see, all of the type of the selected placements have been changed to construction point joint. Similarly, for example, if you want to rotate the placements with a certain angle, you just simply type in 15 degree, for example, for rotating the placements about the local Z. And what you can see on the screen is that the selected placements has been rotated with 15 degrees. This option could be very important for us later because we can work in the plane of the placements. So if you define precisely the placement location and the rotation of the placements, basically you set up a local plane in which you can work very easily. For example, a definition of a complex supporting system at a placement is very easy with this approach. Now I'm going to set back all the local rotation to 0 and type of the placement to be equal with none. And then I'm going to click on the OK to accept the changes and also to visualize the placements. Now it seems that the placement hasn't been created, but if we go to the isometric view, then you can see some colorful squares that are showing the supports. The placements marked with dark blue color are representing the support placements, and all the other type of placements are marked by yellow color. Now, maybe with the help of this square representation of the placements, you can easily imagine the planes of the placements in which we can create complex supporting systems. And this is exactly what we are going to do a little bit later on. But first, I would like to talk a little bit more about the variables. As I mentioned, we need to set up a variable with which we can control the non-effective width of the cross-section. To be able to visualize this non-effective area and the variable a little bit better, I came back to the cross-section editor, and I will show you how to define a non-effective area in the cross-section. Here in the common element chapter, we can find this non-effective parts definition with a diagonal. This is what we are going to do. I'm just going to click on the diagonal. I will explain later the dialog box, but now I'm just going to draw an area with a diagonal that is going to be non-effective. And the reason why we need to set up a variable, which is going to be called NEFF, is to control the dimension measured from the center point. If we measure the overall width of the cross-section with the help of a dimension line, then you will see that the total width of the cross-section is 3000 millimeter. So what we are going to set up together is a variable, and the variable is going to be changing from 2300 millimeter up to 3000 millimeter. And with this variable, we are going to be able to control the width of this non-effective area. Okay, so now I'm going back to the definition of the variable. I will delete everything from the cross-section that I don't need and simply click on the close button, and I will choose discard the changes in the cross-section. And now I'm going to open up the axis definition and double click on the variables. In this dialog box, we can set up any new variables that is referenced to the axis. So I will simply click on the plus sign, and then I will double click on the name and add the variable name hash NEFF. So it means the name of the variable is nef, and the hash is for the definition of any variables. The unit that I'm going to define this variable will be in millimeter, so it is fine. And as you can see, by default, the software already shows me the station values that I had created previously. Okay, now I will multi-select with the help of my Shift button all of the station values, and I'm going to change the value of the nef variable to be equal with 3000 millimeter, and then click. Now the value changed to 3000 millimeter at every station. And now I would like to choose the middle 3 stations, so the middle support and the station before and the station after, and I'm going to override the 3000 millimeter to 2300 millimeter and then click outside. Now you can realize that the value of the nef variable has been changed. Maybe it can be better visualized if you change the scale a little bit with this slider. You can change the scale. And you will see as I click through the stations that at 10 meter, at the axis at the beginning, the value of the variable is 3000 millimeter, then 3000 millimeter, and then it starts to change from 3000 millimeter to 2300 millimeter, then it stays there, and then it goes back to 3000 millimeter, and so on and so forth. And now you might be able to imagine how the non-effective area will change along the bridge. So actually at the beginning there is no change, the total width will be working, then the total width is going to be reduced to 2300 millimeters, stays there for a while, then it goes back to the total width again and stays there until the end of the bridge. Okay, and basically we are done with the definition of the non-effective area variable. One additional thing that I would like to mention is the following, that the transition can be changed from polygonal to transition left or transition right or to a spline. So for example, if I change the transition left here, you can see that instead of the polygonal, I have a transition from the left side, and I can control this transition with a given value, but I can also choose a spline transition if I want to, and so on and so forth. Most of the cases we are using the polygonal transition, and we add as many stations as it is necessary. Okay, finally let's click on the OK button to define the non-effective variable, and then save our project with the help of the keyboard shortcut Ctrl S. This is for quick save. As you can see, I have saved my project. The last thing that I'm going to mention later on is the definition and the usage of secondary axis, but this is going to be at the end of this chapter only. Now let's move on to the definition of the structural lines along the axis in the next chapter. So as I mentioned, in this chapter we are going to define the superstructure in the form of structural lines. Then we are going to export the model, which means we are going to mesh the superstructure, and the structural elements are going to become finite elements. You can undertake the definition of the structural elements on the Structural Elements tab. So if you click on that, you will see how to create and modify the structural elements. On the left side, we can create the structural entities such as structural point, structural lines, and structural area. Whereas on the right side, we can edit or change the already created structural elements. Please also notice that on the left side, below the main structural entity commands, we are going to find some sub-commands. For example, if we have two structural points, we can create a link or a constraint in between them. Also, if we have two structural lines, we can create a link or a constraint between them, or a rigid frictional interface between them. So the main structural element command has, let's call them subcommands as well. In this particular example file, we are going to model our superstructure in the form of a beam element. So we are going to use the structural element line. If we click on the structural line, then a new dialog box, the structural line dialog box, will appear. Let's go through the tabs of this dialog box, starting with the General tab. First, you need to add an identification for every structural lines in the form of a number. Of course, it is done automatically by the software, but if you want a specific number here, then you can enter the desired value in this field. It is also very important to assign our structural lines into groups, because we are going to use the construction stage manager, and we want to activate or deactivate a certain part of our structure. Therefore, here I would like you to type in 20, because the superstructure is going to be activated in construction stage 20. In the next line, you can check in the increase group number automatically. This means when you create your next structural line, the group number will be increased automatically by 1. In this case, we don't need that, so just leave it as it is. You can also add a name to your structural line if you want to, and you can also add a support width to your structural line. This is necessary when you want to activate or define bedding along the structural line, because the bedding is going to be added in the form of springs, and the springs has a certain spring constant, and the value of the spring constant is in kilonewton per cubic meter, and it's going to be multiplied with the support width, and this is how you're going to get the kilonewton per meter run for the final value of the springs. Let's have a look at the next tab, which is the beam cable tab. With the help of this tab, you can create a beam element or a truss element or a cable element if you want to. But it is also possible just to simply define a structural line without any cross-section. In our case, we would like to define an eccentric beam or pile element. As you remember, in the cross-section editor, we defined the position of the cross-section relative to the origin of the local y and z coordinates. We did it because we wanted the cross-section to be inserted as an eccentric beam. After having selected the eccentric beam or pile type, then you need to select the cross-section to be assigned to this structural line. Please notice that you can also enter or add different type of cross-section at the starting point of a structural line and an end point of a structural line. If you do so, then a linear interpolation between the starting cross-section and the end cross-section will be performed. We do not want to do that in this example file, so therefore the start and the end cross-section of the structural lines will be equal with the master section. You can also add variable bedding along a structural line. If you create a bore profile, then you can assign its properties, its bedding properties to the structural line. Also, you have a lot of meshing option or meshing properties regarding the structural line, which I'm not going to explain now in detail. Maybe later on, when we run into any of them, I will explain a little bit. Instead, let's go and move further on to the beam hinges. With the help of this tab, you can create hinges at the starting point or at the end point of the structural lines. You can create these hinges according to the 6 or actually 7 degrees of freedom, or even you can set up a workflow to mimic the behavior of the hinge at the end or at the beginning of the structural line. On the next tab, which is called Support Conditions tab, you can define fixed support conditions along a structural line. Here you can do that in the global coordinate system or reference to the global coordinate system or reference to the local coordinate system of the structural line. A fixed support definition again is possible in the 6 degree of freedom. On the bedding registry tab, you can create not fixed but elastic support along a structural line. You can even add a group number and assign these springs along the structural line into a group. You can also select the direction of the spring element in the global or in the local direction. And of course, it's also possible to set up a torsional spring along the structural line or to create a workflow for the springs along the structural line. In our example file, we don't need to do that, so I'm going to simply delete the created selected line. On the lower and upper wall registry tab, we can do very similar things what we can do on the bedding tab. Namely, we can use this tab as a hand calculator to calculate the stiffness of the springs along the structural line. For example, if I click on the lower wall and the vertical element, I need to choose a material that is mimicking the underlying wall of my structural line. I need to enter a thickness and I need to enter a height of the underlying wall, for example 3 meters. And as soon as I entered these values, a spring constant will be automatically calculated. As you can see here, preview of the stiffness value, and if you want, you can accept this and use it as a spring along the structural line. If you click on the rotational checkbox, then another spring element will be created along the structural line with a different stiffness value. If you also have an upper wall coming to the structural line, then you can also define a rotational spring for this upper wall in the very same manner. Of course, we don't need this in our example file, so I'm just going to simply uncheck the checkbox. On the Interface Elements tab, we can create interface between the structural line and the soil structure. This is for soil mechanics problems, and we are not going to cover it in this course. So all in all, we do not need to specify too many things in the structural line dialog box. We just defined or changed the group number of the structural line and the beam type to be equal with eccentric beam or pile with the master section. And now we are ready to create the structural lines. By default, we are in the polygonal mode. This means that if I click once and twice, then a structural line will be created. However, there are other options to choose from. For example, select an object, segment on an axis, pick lines or curves, single element mode, and so on and so forth. You can come here and click either of these, or in the working area or the graphical user interface, we can simply use our right mouse button to choose from the drop-down list. And in this case, we would like to choose the segment on axis option because we would like to define our structural lines to be assigned to the axis. So if I click on it, then I have a question or a help from the software which says, please pick a segment on an axis. And if I move my mouse closer to the axis, and if I move my mouse closer to the axis, then I can select the axis very easily, and I will click. And now I have two options for creating the structural elements. I can create them between all the placements or use the segment closest to the picked point. Because as I mentioned, the software automatically recognizes the placements along the axis, and because I have clicked in between two segments, it is also possible to define a structural line only between the closest segments. In this case, it would be this one and the other one. Of course, this is not what we want. In this case, we would like to create our structural line between all the placements, and therefore I'm going to select this option. And as you can see, now the structural line has been created. If we zoom in a little bit, you will see that really between all the placements, the same structural line has been created. I'm still within the definition of newer structural lines or further structural lines. If I want to terminate the command, I just need to simply click escape many times, and then I will terminate the command. In the coming step, I'm going to export the model, which means I'm going to discretize the model, and from the structural elements that we have created here in SOFiPlus, I'm going to get finite elements. In other words, from the structural lines, I'm going to get finite element beams. You can undertake this procedure if you go to the next, the second icon from the left, which says create the calculation model by exporting the structure, generating loads, pre-stressing, etc. If we click on it, a new dialog box, the Export dialog box, will pop up. In the Common tab of this Export dialog box, we can choose what we would like to export. By default, normally we mesh the entire system that we had just created. But for test purposes, for example, we can only mesh a portion of the system by choosing the Mesh Partial System, then clicking on this Select Object icon and fencing the structural elements that we would like to mesh or export. Now in our case, we are going to mesh the entire system. You can also choose what you would like to export, because it's also possible to export only the system, meaning the structural elements, but the loads. Sometimes this option is also very beneficial because exporting the loads might take several seconds. But please make sure when you really have loads on your structure, this load checks box is turned on again. The next chapter here is the element type. If we had structural area elements in our system in SOFI Plus, then we can mesh them with quadratic elements or triangle elements. I suggest you to use the quad elements as it is set by default here as well. We can also change some meshing parameters below. First, we can control the mesh density. By default, the density is determined automatically from the extent of our structure. But if I want, I can also set it manually in meter. This means the maximum element lengths within the structure will be equal with the given value. As it is mentioned here as well, set the maximum allowed lengths of a beam or an element edge. Again, I suggest you to do and go with the automatic settings. Normally, it gives a very good meshing result. If you do not like the results of the meshing, then you can refine it with the help of these below 3 sliders. The first one set the refinement around short edges, reduces the element size in the vicinity of short lines. The second slider refines the mesh around the structural points. It reduces the element size in the vicinity of the corners of a structural area. And finally, the third slider is an overall progression factor with which you can actually describe the zone that you would like to perform these refinements. It increases the zone of influence of the local refinements. So basically, this is the way how you can control the meshing. And I would like to also mention the next tab, which is the text output tab. Here in this tab, you can control the output of the meshing within the report browser. By default, the materials, the cross sections, the structural elements, and the loads will be printed in the report browser. But if you want, you can add additional information into the report browser, such as information about the nodes, area elements, beams, and so on. I can also say here that the normal output of the report browser is sufficient. Okay, then simply click on the OK button and see the meshing procedure. Now you can see SOFI Mesh C and the module Aqua were working in the background, and the meshing procedure is over, and we can have a look at the result. If we go to the SOFI Plus toolbar and click on the butterfly icon, which opens the interactive system visualization. Let's do so and see our exported meshed model. So in the system visualization, you can have a brief overview about your structure. Now we can really see that our structural line is meshed into finite element beams. And if we select any of the beam elements by double clicking on it, we can have a look at the beam number and its properties. For example, it's very interesting and useful to have a look at its number first. We can see 2, then 4 zeros and a 6. Basically, the 2 first number is created from the group number. We assigned the structural line to be defined in group 20. And hence, now we see the number of the beam element starting with 20. Then we can see 4 more digits, 10, 20, 30, and the 6. This is because at the beginning we set the group divisor to be equal with 10,000. So it means in one group we can have 10,000 elements, and the numbering is starting from 0001. And this is the 6th element in our group 20. The other important property that we can recognize is the cross-section number at the beginning at the end. Also, you can realize that this beam has been created from structural line number 2, which is correct because the first structural line is between the start of the structure at the beginning until the first support placement, and the second structural line is from the first support placement until the coming placement. So structural line number 2 is correct here. We can also double check the group number, the material that this beam element is made of, and then the nodes that this beam element lies between. Okay, after having overviewed the meshing procedure and the finite element mesh of a structure, now we can create the non-effective area in the cross-section in the next chapter. So in this chapter I'm going to show you how to create the non-effective areas in the cross-section, and that's why we came back from the system visualization to the SOFiPlus user interface. Here in the SOFiPlus user interface we need to go and click on the System tab to go and open up the definition or editing of cross-section number 1, which is called Master Section. I double-clicked on it and I am directed back to the cross-section editor. This is the right place where I can create my non-effective parts in the cross-section. As I mentioned in the previous chapter, we are going to create a non-effective area on the flanges of the cross-section, and we would like to control the position of this non-effective area with the help of the variable that we already assigned to the axis. However, we also need to connect or import this variable into the cross-section properties. So that's why we click on the cross-section properties button and we are directed back to the section properties dialog box. On this dialog box, we are going to find the variables tab as the very last tab. And in this tab, we have the opportunity to import any of the variables that we had created previously in our project. We can do it simply by clicking on the import button, and the created axis with its name is appeared together with the available variables that can be imported. Since we only have one variable, it is only selected. It's already selected for us. Then we just need to simply click on the Add to Section button and it is added into the section properties. Now we can close this dialog box. Now we can check the name. Yes, it's the non-effective area variable. The unit is corresponding to the definition of the cross-section, which is also in millimeter. And in the comment, we can add any kind of comment if we want to, but by default it says imported from the axis called axis. If we had any other variable that controls, for example, the height of the cross-section or the width of the cross-section or any other property, then we should also import here those variables in this dialog box. Since we only define this very variable, I'm going to leave this dialog box by clicking on the OK button. To define a non-effective area, we need to go to the Common Elements chapter, and here we can see two options: non-effective parts definitions with a line and non-effective parts with diagonal. I'm going to use the second option and later just going to partially mention how it's working with the line definition. So now I will click on the diagonal and a new dialog box will pop up. Here first we can add a name for this non-effective area. Let's add the name NEF left, non-effective area left. Second, we can choose which material we would like to apply this non-effective area on. It could be very useful, for example, when you have an in-situ concrete part on top of this bridge deck made out of a different material, and then you make a non-effective area over more materials, then you need to instruct the software which material to be used for this non-effective part. In this simple example 5, we don't have this in-situ concrete deck slab, only one material, so we can check out this checkbox. Also, we need to instruct the software which internal force we would like to omit in the non-effective part of the cross-section. Or we can also say not taken into account in the non-effective part. However, if we want to, we can also omit or neglect the normal force and the secondary bending moment within the non-effective part of the cross-section. This is not the case in our example file because we would like to only neglect the primary bending due to the shear lag effect over the support. However, what we also would like to set is to apply the non-effective property on the reinforcement that falls within the non-effective part too. However, what we would also like to be set is to apply the non-effective property on the reinforcement that falls within the non-effective part. And that's why I'm checking this checkbox. If we had construction stages in our cross-section, then we can also set from which construction stage until which construction stage the non-effective area should work or should be active. Okay, as now we are ready with the settings, now we just need to draw this non-effective area. So I will move a little bit my dialog box and then I will click to the top left part of my cross section and I will draw this non-effective part with the help of a diagonal. And what I would like to achieve is to draw a diagonal which is roughly here. So I would like to make sure that my diagonal is a little bit below this polygon point. So I will click somewhere here. And then I will click Escape and then that's it. We have defined the non-effective area on the left side of the cross-section. Let's do it on the right side as well. So again, I will click on the non-effective part diagonal. I will simply add the name non-effective area on the right. I will also check in this checkbox. That means the reinforcement is not going to work within the non-effective area. And again, I will click with my cursor somewhere here and I will draw the diagonal like this and then click on the escape button. And again, let me visualize how the variable is going to control the area of the non-effective part. So actually I'm just going to select it and with the help of stretching I will like to show you that basically normally far away from the support the non-effective area will be somewhere here. So it means that the whole cross-section width will work, whereas over the support the variable value will be set in such a way that the non-effective part will be somewhere here. So as you can see, a great part of the cross-section is not going to work over the support. So now we just need to control the width of this non-effective part with the help of the variable. And this is what we are going to do with the help of this chapter called parametrics. With the help of parametrics, we can create references, or I would say rather constraints within the cross-section, but not statical constraints, but geometrical constraints. And let me show you how to do that. If you click on the Cartesian references command, then you will see a text line in the command line which says specify constraint point. What you need to do is to specify the point that you would like to reference. In our case, it is going to be the bottom right corner of the non-effective area. If you click on it, then the command line will change and say to you specify reference point for horizontal distance, and there is a suggestion which is the 0 point of the local coordinate system. You can choose any of the points from which you would like to reference your original point, but in this case I'm just going to simply accept what the computer or the software suggests to me, which is the 0 point of the coordinate system, and therefore I'm going to click or hit the enter button on my keyboard. Now the message in the command line has changed again. Now the software wants me to specify a reference point for vertical distance, and it suggests me the 0 point again. I will also accept this with hitting the enter button on my keyboard. Now, as you can see, it seems like we did a dimensioning of this point on the bottom right corner of the non-effective area. But this is a very special dimension line because we can overwrite its value if we click on this small lock symbol. If we do so, we can see the exact value, and if we simply click on the lock symbol here again, we have the possibility to override this value. Let's do it together. I will enter value. This dimension should be equal with minus hash and non-effective. So, and then I will click on the check symbol, and as you can see, the real value of this dimension line, or now I would say the real value of this Cartesian reference line, has changed to be equal with the negative value of the nef variable. Here, of course, the vertical value is irrelevant, so I'm not going to change it at all. We need to repeat the same procedure on the right side. So I'm going to click on the Cartesian references command again, and I will simply choose the bottom left corner of the right non-effective part. And then now I need to specify the reference point for the horizontal distance. I will hit the enter button. Also, I need to specify the reference point for the vertical distance, but I will accept what the software tells me. So I will hit the enter button again. And now the second Cartesian reference has been created. I will click on this small lock icon and here again, and I will add equal hash, and as you can see, there are already predefined variables in the system. You don't need to pay attention to it. These two variables are always defined in every model. So you just need to enter equals hash NEFF. So it means that the horizontal distance will be equal with the variable nef. If you want to change the value of an already defined Cartesian reference, you need to come closer to the reference point, and then if you hover over your mouse on this reference point, then you can easily select it. So I always suggest you to zoom in, and then you can have a clear selection. What we need to create in this cross section as well is the following. As you can see, now the stress points are within the non-effective area. And this is not what we want, because over the support, when we really have a width of this non-effective part, then the structural point is going to be really within this area. And then we are not going to receive any stress. So to get over this problem, we need to parameterize the position of the stress point too. The procedure is of course the same. We would like to use the non-effective variable to control the position of the stress point along the top fiber of the cross-section. What we need to pay attention to is the following. We need to make sure that the stress point is always outside the non-effective area. So the way how we're going to define the stress point is that we are always going to deduct 10 millimeter from the non-effective variable value. In this way, we can be sure that the stress point location is always 10 millimeter away from the fiber of the non-effective area. Okay, let's do it with the same Cartesian reference approach as we did. I will click on the Cartesian references. I will zoom in to be sure that I'm selecting the stress point, and I will hover over my mouse to the blue stress point and then click. And now the software will ask me which point I would like to select, whether the polygon point of the cross-section or the stress point. I will select the stress point, of course. Now the software is asking me to specify the reference point for the horizontal distance, if it is different from the 0, point of the coordinate system, but I will accept the suggestion from the software and I will hit 2 times the enter button. And as you can see, now the Cartesian reference has been placed. The same procedure is applicable like previously. I just need to click on the unlock symbol and here again to the unlock symbol, and I will add the following expression: equals minus hash non-effective plus 10 millimeter, and then I will accept this. So let's consider together. So the position in the horizontal direction of the stress point will be equal minus the non-effective variable plus 10 millimeter. Of course, the same setting needs to be done for the right side. So I will click on the Cartesian reference again. I will zoom in, select the stress point, and then I will accept the reference to be equal with the origin of the local coordinate system. I will click on the lock symbol 2 times, then I will add here equals hash non-effective variable minus 10 millimeter, and I will accept this. Okay, now it seems that we add all the parametric references or the parametric constraints in the cross-section. I just would like to mention a very important information as well when we have multiple points intersecting each other at one location. For example, here, if I want to make a reference or a constraint where the horizontal line reinforcement, the vertical line reinforcement, and the singular reinforcement intersect each other. It is a very unique position within the cross-section, and if you want this point to be parameterized, then you need to apply the Cartesian reference command 3 times, because if I come to this position and select a point, actually I have 3 possibilities to choose from. I can parameterize the endpoint of the vertical reinforcement, but I can also parameterize the endpoint of the horizontal reinforcement, and so on and so forth. And for this reason, I need to set up or define 3 Cartesian references. This is what I wanted to mention, and it is very important in your future work. So now we can leave the cross-section editor by clicking on the close button and accept the changes. And now we received the warning message that I'm going to explain and we are going to deal with. So the warning message says the stress point called top left in cross-section number 1 in construction stage 0 is inside of an non-effective area. We can ignore this message and I'm going to show you right away why. First, let us export the model by clicking on this export button and clicking on the OK button. We will see our structure in the system visualization, and if I zoom in, now we can really see the non-effective area working perfectly. First, let us export the model by clicking on the export button here in the top part. Fortunately, it seems to me everything is working fine or as we expected. The non-effective part changes the width along the lengths of the axis. We can also make sure that everything is fine if we go back to SOFI Plus, and instead of the system visualization, we choose to see the results in the result viewer by clicking on this button in the top line. Now the result viewer will be open for you and we can have a look at the cross sections. At the moment we are viewing the master section with number 1. If we want to see the other sections, we just need to click on the next one. Since we defined a variable along the axis, now interpolated cross sections has been created, and this is what we can see if I click on the next button. Now I can see cross-section number 2, but if I click further on the next one, now I'm going to see the first interpolated cross-section with number 101. If I click on the next again, now I can see 102, and I can also see the development of the non-effective area in the cross-section. If I now click on the next, now I can see the cross-section with number 103 and with the full length of, or the full width of the non-effective area. If I choose the presentation of the stress point within the cross-section, then you will see that everything is fine with the definition. If I select the stress point name to be presented and click OK, now I can really see that the top left and the top right stress points are really not within the non-effective area, but they are 10 millimeter away from the edge of the non-effective area, which is what we wanted. And if I go back in the interpolated cross sections, 102, the same is applicable. The top left stress point is outside the non-effective area, so everything is fine. In construction stage 101, everything is fine again. The top left stress point 10 millimeter away from the edge of the non-effective area. And now if I go back to the master section with number 1, I can find really the top left point is within the non-effective area, and that is why I received the warning message. However, this cross-section is not going to be used in my superstructure. I can show it to you if I go back to the system visualization and click any of the beam elements here. You will see that I'm using cross-section 101, 101, 101, and when the interpolation reaches the start of the non-effective area, then I can find a beam element whose cross-section at the starting point is 101, but at the end point is 102. Then I can find another beam element with cross-section 102, 103, and so on and so forth. So what I wanted to show is that all along my superstructure, I'm using the interpolated sections from 101 to 103, and therefore the warning message regarding the master section number 1 can be ignored. To have the full picture of the meshing procedure, You can also verify your input in WinGraph. If you go back, or if we go back to SOFI Plus, here we can also start and review the meshing procedure and the defined elements within WinGraph. If you click on this icon, then WinGraph will be opened. It's on my other screen, so I will drag it here. And now we are in WinGraph. I will explain later how this program works, but for now I would like to show you the number of the cross-section along the axis. If we go to the system values and select the beam elements, and in the beam elements chapter we select the number of cross-sections, then the number of the cross-section will be presented along the axis or along the beam elements. As we zoomed in a little bit, we can see the numbers maybe with a little bit smaller text, and this is what we are going to find. Basically, we can see very nicely the changing of the cross-section numbers, first starting with 101, then from station N1 to station N2, it develops up to 103, then it stays there, and then it goes down from station N3 from 103 to 101, and then the number stays on 101. Okay, so as you can see, WinGraph is another tool with which you can check your input and output as well. So now I would like you to close back all the other programs that are open except SOFI Plus. So I will close back WinGraph without saving. Then I will also close back the system visualization. Then I will also close Result Viewer without saving the changes. And now I am back to SOFI Plus. The next step in our model creation will be the definition of the supports with the help of the cross-member editor in the next chapter. In this chapter, we are going to create the support conditions, basically the supports of the superstructure together. To do that, I need to introduce you the cross-member editor. If you zoom in to one placement, then you can see the name of the placement if you hover over your mouse over a placement. And basically, with this movement, we select the plane of the placement. However, if I double click on a placement, then I'm going to be directed to the so-called cross-member editor. What is this and how does it work? The cross-member editor basically shows the plane of the placement for us. I am looking at the local Y and Z coordinate system of the cross-section, and perpendicular to the screen I can see the local x-axis of the beam. In this case is the same direction as the axis of my superstructure. In the cross-member editor I have the opportunity to create or model any kind of structural elements to my model as well. For example, I can define a fixed support at the origin of the local Y and local Z coordinates to support my superstructure. However, before we do the supports to our superstructure, let me go through the opportunities in the cross-member editor. If we go and open up this jump to placement, we have a drop-down list where we can see all the placements that we had defined previously. With light blue color, you can see the support placements, and all the other type of placements are marked with yellow color. So you can select simply any of the placements, and basically with this opportunity you jump between the placements. An alternative way to going through the placements is using these arrow buttons. As you can see, when I'm clicking back, I'm going back in the station values, I'm going backwards in the stations. Next to the placements, we can see the thickness value being equal with 0.5 meter. This means that the depth that I am looking at the moment on my screen is equal with 0.5 meter. In other words, the thickness of my view currently is set to 0.5 meter. So I can see all the elements within a thickness of 0.5 meter. Now I will try to visualize this thickness to you with rotating my model. So I will simply click my Shift button and my middle mouse button. And as you can see, I was able to rotate my model into an isometric view. And now you could maybe imagine it better that the thickness of 0.5 meter means that I could see every structural element within 0.5 meter thickness in the local X direction. Okay, now let's close back the cross-member editor and go back to the original model. Because now I would like to explain a little bit about the support conditions of the superstructure. Therefore, I have created a small sketch without scale how the support scheme is look like for this particular bridge. So here you can see the global X and global Y coordinate system. So this is the longitudinal direction of my bridge. And here you can see 6 elastomer bearings. Over the pier, I have my very one fixed bearing. This means that this bearing is fixed in the longitudinal and in the transverse direction. At the beginning and at the end of the structure, in this plane, I have 2 bearings which can move in the longitudinal direction, but they cannot move in the transverse direction. Over the middle pier, but at 1800 millimeter away from the fixed bearing, you will find a movable bearing which can move in the transverse direction, but it cannot move in the longitudinal direction. These 2 bearings are over the middle support, the pier. The cross-section of the middle support is 2200 millimeter wide, so it has enough space to accommodate these 2 bearings. Finally, you can find 2 elastomer bearings at the beginning and at the end of the superstructure, which are movable in longitudinal and in transverse direction as well. This same scheme can be seen on the training example drawing. If you look at the top view, you will find these 6 elastomer bearings, 2 at the beginning, 2 over the middle support and 2 at the end. If we zoom in a little bit, you will also find this 1800 millimeter between the bearings at the beginning, also over the middle support and at the end. Please also notice one very important thing. On the side view, if I zoom in, you will see that between the superstructure and between the top of my pier, there is 20 centimeter space, which means that the height of my elastomer bearing is 200 millimeter. This is something that I would like to take into account because it makes a very important movement for my superstructure at the beginning and at the end. For example, at the beginning of my structure, if I let the superstructure move in the longitudinal X direction and I have 20 centimeter gap between the support and the soffit of my superstructure, then from a vertical load there will be a horizontal movement of my superstructure. And this is an effect that I would like to consider as well. And therefore, this is the final scheme of the support condition that I would like to create in my model. I have the origin of the local Y and Z coordinate system here, where my mouse is at the moment. This is also the reference point of the cross-section. And from this point, I would like to take down all the effects into this point with the help of the so-called couplings, which are drawn now by red. And I will define then 20 centimeter long spring elements, real spring elements, to mimic the behavior of the elastomer bearings. These springs elements are 1800 millimeter away from each other, and at the one end of the spring elements I'm going to introduce fixed supports. Or at the middle support where my pier is, I will simply connect the spring to the end of my column that is representing the pier of my structure. Okay, let's move on and create this solution in SOFiPlus together. So what we need to do is double click on the first placement, and then we are going to find ourselves in the cross-member editor. An important thing to mention here is in cross-member editor, we are working in meter, not like in the cross-section editor, where we are working in millimeter. So the first thing that we are going to define is we are going to add two structural points to our model, which are going to be the top fiber and the bottom fiber of the elastic bearing. We can define the structural points with the help of the Structural Elements tab, and we can find the definition of the structural points at the top of the Create and Modify chapter. If you click on the structural point, a new dialog box will appear. Let's go through the tabs of this structural point definition dialog box. In the first line, you can identify your structural point with a number. If you want, in the second line, you can add a name to your structural point. If you enter a value for the slab thickness, you have the possibility to control the thickness of quad elements. For example, if you have a squared shape quad element and you defined 4 structural points at the corner points, you can set a different thickness in the structural point dialog box here at the slab thickness, and the thickness of the quad element will follow this input. Also, there is an opportunity to add dimension for the punching design later on at certain structural points. In the next tab, in the support condition tab, we can define support conditions to our structural points. We can also add and define springs to our structural point. And similarly, what we saw at the structural line, we can add axial springs or torsional springs, and we can define them with a constant elastic stiffness value, or we can also set up a workflow for them. Again, very similarly to the lower and upper wall at the structural line, here we can model a lower or an upper column at a certain structural point. As I mentioned at the structural line definition, basically we can use this opportunity as a calculator from the software, where we just need to set up the material, the lengths of the column, and the fixity, and a certain value will be calculated and used as a spring element at the structural point location. We can also define structural points as a pile in the half space, but we are not going to deal with it in this example file. And finally, we can also define loads at the structural points. However, in this example file, we do not need any of them. We just simply want to position a structural point, and I'm going to do that by simply selecting the bottom left corner point of my superstructure, and I will click, and as we can see, a new structural point has been created. I will terminate the command by pushing the escape button on my keyboard. The structural point is not at the right position, so I would like to move it. We can move any structural entity if we go to the top line where we can find the commands, and in this case we choose the move. Click on it, and then we need to select the object, in this case our structural point, and then click enter. Now the software wants me to enter the base point of my movement vector. So I will simply click anywhere in the graphical user interface for the starting point of this vector. And now the software wants me to specify the second point of this vector, which is going to be 0.2 meter away in the horizontal direction. So I start to move my cursor into the right side and I will type in 0.2 meter and I will hit the enter button. As you can see, now the structural point moved 0.2 meter away from the corner point. This is what we wanted actually, because the overall width of the soffit of my superstructure is 2.2 meter. And if I move my structural point 0.2 meter on both ends, then the distance between the structural points will be 1.8 meter from each other, and this is the distance that I would like to achieve. Now we just need to copy this structural point in the direction of the local Z axis. I will do it simply by choosing the copy command, and then I will select the structural point and then hit enter. Now the software wants me to specify the base point of the copy vector. I will do that by simply clicking anywhere in the graphical user interface. Then I will move my mouse downwards and simply type in 0.2 meter. And the copy has been created. Now I will push escape on my keyboard to terminate the command. So now I was able to create the top and bottom point of my elastomer bearing. Of course, we are going to set up the support condition only of the left side in my cross section, and then I will mirror the whole system to the right side of the cross section. First, let's make the bottom point of the elastomer bearing fix. You can do that if you simply zoom in a little bit and select your structural point by double-clicking on it. Then you are going to be directed back to the definition of the structural point. Here, if you go to the support conditions tab, then we can set up the support conditions in the global coordinate system, and we're simply going to come here and select the all, and in this way all the support conditions has been turned to fixed. Now we just need to leave the dialog box by simply clicking on the OK button, and if we zoom out we can see what happened. The bottommost structural point has been fixed in every direction. In the next step, I will continue with the definition of the couplings between the reference point of my superstructure and the top point of my elastomer bearing. A coupling, or in this case, a point-to-point constraint, is capable of transferring the deformations between 2 points. So what I'm going to do now here is to define a coupling between these 2 points, and the deformations from this point will be transferred over to this point. Okay, let's get simply click on the point constraint command, and then you will find yourself in this dialog box. First, you need to add a group to the newly created constraint. We are going to enter 20 because this is also the number of the construction stage where we want to activate this coupling. By the way, this is also the construction stage where the superstructure, our structural lines, and then finally the beams will be activated. The type of the constraint can be global or can be local. If you select local, then the local degree of freedom will be selected. Now we go with the constraint type global. And now I will click and choose the top point of my elasto bearing first and click. And for the second time, I will select the origin of my local coordinate system and click. Then I will enter or hit the escape button on my keyboard to terminate the command. As you can see, the coupling has been created with a beginning point. You can see number 1 here and an end point with number 2. The numbers here are playing a very important role. Point number 1 is the so-called slave node, and point number 2 is the so-called master node. The reason why we call them in this way is because one master node can have many slave nodes, but one slave can belong to only one master node. And in our case, I would like to couple another node from this position to the very same origin point, and that's why it's important that the origin point is going to be the master node of my couplings. Now I would like to mention that it's not necessary to have a structural point defined at the position where I click and define my coupling. It will be done automatically by the software. For example, in this case, at the master node, a new structural point will be automatically created. The same principle is applicable for this location as well. I shouldn't have defined this structural point beforehand. However, in this case, it is very useful and necessary to have this structural point because I would like to define a spring element in between these two structural points. And the orientation of the spring element is based upon the firstly selected structural point. In my forthcoming spring definition, I will select this structural point to be the beginning point of my spring. And when you double click on a structural point, then the local coordinate system of this structural point will be visible for you. Now we can see, for example, the local y coordinate of the structural point is pointing to the right side on my screen. The local z coordinate of the structural point points downwards. And from these two directions, with the help of my right hand, I will be able to conclude that the local x coordinate, or the local x-axis of my structural point, is perpendicular to the screen and pointing away from me. The color scheme of the local coordinate system is always going from the warm to the cold. This means that local x, y, z and the corresponding colors are red, green and blue. So the orientation of the local coordinate system of the structural point is going to be very important for us when we are defining the spring elements between these two structural points. And now you will understand when we, for example, set up a new spring in the local y direction, which direction this newly created spring points to. Okay, now I will simply unselect the point and I will continue with the definition of the springs between the two structural points. So now in the next step we are going to use the point-to-point link, which can be found below the definition of the structural point. If I click on this command, then a new dialog box will appear. And first, I'm not going to set any special property to the spring, just simply first define one spring between the structural points, and then I'm going to edit the properties of this spring. So as you can see, first I need to click the first point, which is going to be the first structural point. I will select it, and then as the second point of my spring, I will select the second node. And now the spring has been created. I will push the escape button on my keyboard to terminate the command. So as you can see, first I need to select the first structural point, which is going to be the top one in my case. So I will simply select it and pick the next point. I will select the next structural point and I will hit Escape on my keyboard to terminate the command. Now I will double click on the created spring element to be able to adjust its properties. The reason why I use this method, namely first define the spring element and then to edit its properties, is because you will see how many properties we are going to set for one spring element. And let's assume that we're done with all the settings here, and then I do some wrong clicking in the graphical user interface, then I need to restart my procedure. So I found it personally a more flawless method to define the spring first and then edit its properties. Before we jump into it, let's have a closer look at this bearing that we are about to define in the support scheme. So once more, I would like to refer to the support system scheme, and in this time we are defining the supporting condition of this bearing. And as you can see, we are going to set up basically 6 small springs in the local X, local Y, and local Z direction, which is perpendicular to the view. And first we are going to create 3 springs against the translation in the local directions, and then other 3 springs against the rotation about the local axis. This means that at this particular bearing, the spring in the local X direction will be free, so a very small value will be defined for the spring constant, namely 1 kilonewton per cubic meter. In the local Y direction, we are going to define a very stiff spring element. In the local Z direction, which is perpendicular to the screen, again, we are going to define a relatively stiff spring element. And against the rotation about the local axis, again, we are going to define a very weak spring constant of the springs. So now let's do it on the editing of the properties dialog box. First, we just need to add a number for the very first spring element. I'm going to use a unique number, namely a 3-digit number. So now let's undertake these settings in the dialog box here. The type of the spring, the first spring is okay. It's going to be an axial spring. We need to specify a number for the spring element. For this, I would like to use a 3-digit number. First, I will start with 101. From this 3-digit number, the first number is going to refer the support plane. So we have along the bridge 3 support planes, one at the beginning, one at the middle, and one at the end. So the first support plane starting with number 1. And the second number will be the number of the springs. The next entry is very important to fill correctly. We need to add the group number to be equal with 20, because we would like to activate these springs together with the superstructure, and the activation of the superstructure will happen in construction stage 20. Now we need to select the direction of the spring. We are going to choose the local X, and we are going to define all of the springs elements in the local directions. Then we need to set up 2 numbers, the axial stiffness for the spring element and the reference area of the spring element. Multiplying these 2 values together will give us the correct unit of the spring, namely kilonewton per cubic meter multiplied with 1 square meter is going to give us kilonewton per meter, which is the correct unit for a spring. You can see on the screen that the local x-axis is pointing in the direction of the bridge longitudinal direction. And as we discussed, in this direction the stiffness should be very small, so I will add the axial stiffness to be equal with 1 kilonewton per cubic meter. And that's all. we do not need to define any transfer stiffness. You can see on the screen that the local x-axis is pointing in the longitudinal direction of the bridge. And as we discussed on the support scheme, we do not need to define any spring in this direction. So the way how I will achieve this is I'm going to add a very small axial stiffness for the spring, namely 1 kN per cubic meter. The transfer stiffness of a spring means the following. Now we defined a spring in the local x direction. A transverse direction to this local x is a plane, which is actually the local YZ plane. Of course, we do not want to define any spring element in this direction because we would like to define springs in every 6 degree of freedom. Hence, we are going to leave the given value transfer stiffness equals 0 kN per cubic meter. Now we need to define the other springs as well. So I will click on the New tab, and a new spring has been added to the definition table. It is also going to be an axial spring element. The number will be 102. The group number will be 20. The direction will be the local y direction, correct. If we look at our local coordinate system, the local y direction is perpendicular to the bridge longitudinal direction. This is the direction we would like to support our structure. So at the axial stiffness, I'm going to use a quite high value. Normally, we should enter an axial stiffness between 1 on the power of 6 and 1 on the power of 8 in kilonewton per cubic meter. Personally, I use always 1 on the power of 6 kilonewton per cubic meter. Again, for the transfer stiffness, we do not need to add any value. We can create the new spring element. It is going to be an axial spring as well. The number will be 103. The group will be 20. The direction will be local Z, which is the vertical direction. And I'm going to enter a value of 1 on the power of 6 again. Now in the next steps, I'm going to define the rotational or torsional spring elements. So I have clicked on the New tab and selected a torsional type of spring element. The number will be 104, the group number will be 20, and the torsional stiffness will be 1 kilonewton meter per radian. Our bearings are elastomer bearings, so they are capable of provide resistance against the translation in the local directions, but they cannot provide any resistance against a torsion about the local axis. Therefore, I am setting the stiffness of the torsional spring to a very small value. Before I move on to the next direction, I need to also set up the direction. In this case, first I define a torsional spring about the local x-axis with a value of 1 kilonewton meter per radian. Now I can continue with creating a new torsional spring. The number will be 105. The group will be 20 again. The spring direction will be local y. And the value of the torsional stiffness will be 1 kilonewton meter per radian. I will repeat this for the very last spring. It's going to be a torsional spring. The number will be 106. The group number will be 20. The spring direction will be the local Z, and the torsional stiffness value will be 1 kilonewton meter per radian. Okay, before I click on the OK, you can have an overview together with me whether or not all the numbers and group numbers and direction are set correctly. So number 101, 20 local X, 102, 20 local Y, 103, 20 local Z, 104, 20 local X, 105, 20 local Y, 106, 20 local Z, and I should see only one axial stiffness value, actually two stiffness value different from one in the local Y and in the local Z direction. And this is the case, so I can simply now click on the OK button. Now, as you can see, the 6 springs have been created. And now all we need to do is to copy over the support condition that we defined for the left side of the cross-section to the right side of the cross-section. The reason why I'm using copy and not the mirror command is I want to maintain the direction of the local coordinate system, and with the copy command I can provide it easily. So I will choose the copy command from the top toolbar, click on it, and now I just need to select all the objects that I would like to copy. I will select the objects by fencing them from the right to the left, and in this way I can select everything, including the coupling, to be copied over. Now I will hit the enter button, and now I just need to select the base point of my copy vector. I will click somewhere on the graphical user interface, start to move my cursor to the right, and I will simply enter 1.8 meter and click on the enter button. Finally, I will click the escape button to come out of the command. Now all we need to do is to select the coupling and grab its endpoint and move it to the other endpoint of the other coupling, and then click once more. And now you can see what I was talking about. Here we have one master node, and this master node has two slave nodes, which is correct. Okay, and now we can have a look at the springs that have been created with the copy procedure. What I can see is that the first number is 107, which is correct because my last spring number on the left side was 106. So 107, then 108, 109, 110, and so on and so forth. The number setting is correct. All of the spring elements are assigned to group number 20, which is also very important. The local X, local Y, local Z coordinates has been kept as well, which is also what I wanted. Now the only thing I need to change is the elastic stiffness in the local Y direction. Why is that so? Because if we come back to our support system scheme, you can see that now we are defining this elastomer bearing, and this bearing is movable in the longitudinal and in the transverse direction as well. So therefore, where we are defining the axial springs in the local Y direction, I must enter a very small axial stiffness, namely 1 kN per cubic meter. So this means that at this bearing, we only have one spring element with a high stiffness value in the local Z direction. Okay, now I will accept these settings by clicking on the OK button, and we are done with the definition of the support condition at the very first support plane. If we look at our support system scheme again, we will find that the support condition at the support plane 3 is also the very same like at the first one. So it would be very time-saving if we could simply copy over all the settings that we did here at the first support plane to the very last support plane. Fortunately, it is possible with our software, and this is what I'm going to show you right now. If we come back to the cross-member editor and you click with your right mouse button, then you will find a clipboard entry in the drop-down list. Please choose the Copy with Base Point option and enter 0, tab 0 and then enter. With this way, we selected the origin point of the local coordinate system to use as a base point for our copy procedure. Now we just need to simply select all the elements that we would like to copy over. I will fence all of the structural elements that I would like to copy over and then click on the Enter button. Now all the structural elements have been copied to the clipboard of my computer. So now what we need to do is to simply choose the right placement where we would like to undertake the copy. And I will choose the placement P4 at station 63.9 meter. As you can see, now there is no structural element defined here at all. Since the structural elements are on our clipboard, I will simply click with my right mouse button, and from the clipboard menu I will choose the Paste submenu. And now the software wants us to give an insertion point, and I will enter with my keyboard 0, tab 0 and enter. As you can see, now all the structural elements, the supporting system, has been copied over to placement P4, and this is what we wanted. However, now we need to overview the numbering of the spring elements, because the numbers will simply continue from 112, and this is not what we want. We would like the spring elements number to start with 3, and then 301, 302, 303, and so on, the numbers that we would like to see here at this placement. So now if I go and simply click on the spring elements number, you will see really the first number is 113, and this is what I'm going to change to 301, and then continue and change the number for all the other spring elements. 303 here, 304, 305, and 306. And then click on the OK button. We need to redo this procedure and override the number of the spring elements on the right side as well. So I will start with simply 307, and then 308, and so on and so forth. 310, 311, and 312. Fortunately, as we saw in the support scheme sketch, the support conditions are exactly the same at the end of the bridge like at the beginning of the bridge. This means that the stiffness value of the springs do not need to be changed. So I will simply click on the OK button now, and we are done with the definition of the support conditions at the last placement as well. Now we need to continue with the definition of the support condition at the pier. Since we had copied over the structural elements to the clipboard and they are still there, we just need to go to the middle placement, which is placement P3 at station 37.3 meter, and select it. Now we are directed to the placement P3. And what we need to do is clicking with our right mouse button, choose the clipboard from the drop-down list and choose the paste. And here again, the software waits for us to enter the insertion point. I will enter again 0 from my keyboard, then the tab button, and then 0 again, and enter. First, now we need to overwrite the numbers of the spring elements. So I will simply zoom in, click on the spring element, and start to renumber the springs from 201, then 202, and so on. (206) is the last one, then I will click OK. The same renumbering needs to be done on the right side from 207, 208, 209, 210, 211, and 212, and then I will click on the OK again. This time the support condition is not the same like it was between placement 1 and placement 3. So now we can go back to the support scheme and see how to set the spring constant. So for the left side, we have a bearing that is fixed in every local X, local Y, and local Z direction. And on the right side, we have a bearing which is fixed only in the local X direction, but free in the local Y direction. Okay, let's do it in the cross-member editor. So I will zoom in to the left side, double click on the spring element, and in local X direction I also need to add a stiffness of 1 on the power of 6. For the local Y direction this value is already entered, and for the local Z direction it's also already entered. So I will click on the OK. Now I will zoom out and go to the right side to set the spring stiffness on the right side. Here the spring in the local X direction needs to be fixed, so I will enter 1 on the power of 6. In the Y direction it should be free, so it's fine. And in the local Z direction we have a stiff spring as well. So now we have all the settings and the changes what we wanted to, so I will simply click on the OK button, and we are halfway through at the middle support. The reason why I'm saying only halfway through is because at the middle support we have a pier, and this is something that we should enter and define in the cross-member editor now. So if we go back to the cross-member editor, we just need to define a new structural line that is going to model our pier element. I will simply go and select the structural line because the pier is going to be made out of a new structural line. On the General tab, first I need to add the correct or the proper group number, which is going to be group number 10. The reason why is because I would like to activate the pier in construction stage 10, one construction stage before the activation of the superstructure. If I entered the group number to be equal with 10, I go to the beam/cable tab and I will select the element type for the structural line to be as cross-section. You might remember that we have defined the cross-section for the pier as a standard cross-section, especially as a rectangular column section. The reason why we did it is because if we choose a rectangular column section and we insert it as a rectangular column cross-section, then the software will know that this is a compressed member, and the minimum amount of reinforcement needs to be considered according to a compressed member and not according to a bended element. And this is the reason why we insert the structural line with the cross-section and with the element type as cross-section. Of course, we need to choose the right cross-section, which is cross-section number 2. These are all the necessary settings that we need to do for this structural line, and now we just need to define it in the cross-member editor. To do that, we simply somehow need to start our structural line between these two structural points. How can we do that? If we click with our right mouse button and together pushed with the control button on my keyboard, then you will be directed to the so-called object snap settings. Here we have the opportunity to choose the midpoint between two already defined points, I will select this opportunity, and first I will click on the left structural point and then on the right structural point, and now I can draw the 4.5 meter long pier, but I need to activate the orthogonal mode by clicking on the F8 button, and I need to move my mouse to do that. We need to somehow start our structural line in the middle of these two structural points. How can we do that? I will click by pushing my control button on my keyboard and with my right mouse button at the same time. And now the so-called object snap settings or object snap panel appeared. I will select the opportunity midpoint between 2 points, and now I will click on the left structural point and the right structural point. Then I will move my mouse downwards, and I will simply enter with my keyboard 4.5 and then hit enter. Then I will click escape to come out of the command. If we zoom out, now we can see that really the pier has been generated in the form of a structural line. However, as we can see, now the pier and the superstructure is not connected, so this is something that we need to work on. First, I will delete the structural point fixities by going to the point, to the structural point. And if I make this dialog box a little bit bigger, on the right side I will find the modify of the properties of the structural point, and I will click on it, and I will select the two structural points, and then I will hit enter. Now I am directed back to the definition of the structural points. And here, as you can see, I can find the support condition for the structural points, which are all fixed at the moment. So I will simply take out all of these and click on the apply and then click on the OK. As you can see, now the fixities of the structural points has been disappeared. So now we just need to connect the end of our pier with the structural points. And for that reason, we are going to use the point constraints once more. Before we do that, let us consider again the coupling conditions regarding the master and slave nodes. So this time, this will be the master node, and these two will be the slave nodes. So let us set up this together. If we click on the point constraint, the dialog box will appear. It is important to add the right group number, which will be group 20, because as soon as the superstructure appears in the construction stages, this constraint needs to be activated as well. So after having added group number 20, I will simply select the left structural point and click on the end of the pier, and then I will select the right structural point and click on the end point of the pier. Then I will push the escape button on my keyboard. If we zoom out, now we can see that the pier has connected to the superstructure, but the pier itself needs to be supported too. This is what we are going to do in the form of a new structural point definition. So I will simply click on the structural point definition icon, and the dialog box will appear. Now the number of the point is irrelevant for us. At the support conditions, I can create fixed support conditions for the structural point. Now, yes, it could be a valid solution to create a structural point with a support condition fixed in every direction. But for later evaluation of our model, I would suggest you to create spring elements with a very high stiffness in every 6 direction, like we did with the springs between the superstructure and the substructure at placement 1 and 3. So I will simply click on the plus icon and I will set up the 6 springs like we did before at placement 1 and 3. Let's start with the axial springs. So first I'm going to create a new axial spring element. The group number will be 10 because this structural point or these spring elements belongs to the substructure, which is going to be activated in construction stage 10. Then I will select the direction to be the local X, and I will add an axial stiffness to be equal with 1 on the power of 6 kilonewton per cubic meter, and no stiffness in the transverse direction as we did before. One other thing that we need to think over is the numbering of the spring elements. If we move the dialog box a little bit to the top, now we can think about the numbering. For the spring elements between the superstructure and the substructure, we used at placement 2 the numbers 201 until 212. And since they were also assigned to group number 20, the real number after the meshing procedure of one spring element here will be something like 20, 0, 201, and the last one 20, 0, 212. So we are going to receive a 6-digit number where the first 2 digits refers to the group number and the last 3 digits will be the number that we gave in for the springs. This is a very nice numbering and we should do and keep it for the spring elements for the structural point down at the bottom of the pier as well. However, this numbering for the structural point springs doesn't work properly yet. We are working on this manner to solve this problem. But at the moment, what we can do is enter the final number manually here in this field. And the final number will be 10, because this is the group number of the structural point or the spring. And then comes a 0 and then 201. So as now we set everything, we just need to copy this line. I will simply click on the new or the plus sign. And as you can see, this line was copied and the number has been increased by 1. So in this case, I just need to change the direction to local Y and then make another copy and then change the direction to local Z. Now I will copy the last line again by clicking on the plus sign, but in this case, the newly created spring is not going to be an axial spring, but a torsional spring. And I will select the direction to be local X and the torsional stiffness to be equal with 1 on the power of 6. I will select the last line and click on the plus sign, and I will change the direction to be local Y. The torsional stiffness value is correct now. I will select the line, click on the plus button, and I will add the direction to be local Z, and the stiffness value is correct. So now we have all the settings that we wanted to for our spring elements. If we zoom in a little bit and select the spring elements or the structural point, the local coordinate system of the structural point will be visible, and we can be sure that the local X, Y, Z coordinates coincide with the local coordinate system of the other spring elements that we had defined previously. Now I will click on the Escape button and show you another interesting thing, which is the following. If you select the spring element by one clicking, you will see a symbol which is not going to be bigger if I zoom in, but maybe you can read it. It says axis, and then you can find a small SOFiSTiK logo above it. This small axis icon means if you hover over your mouse, linked to placement P3 on axis. So if an element is linked or assigned to an axis, then it means if you change the axis geometry, then this element, because it is linked to the axis, is also going to change automatically together with the axis. This is what we call the CABD technology, so computer-aided bridge design, and it is very useful for us because, for example, just try to imagine that our axis of the bridge now is straight and the local y coordinate of the structural point is perpendicular to this axis. As soon as I change the axis of the bridge to be a curved shape axis, then the local y direction of the local coordinate system of the structural point will also be perpendicular to the axis. And with the help of the usage of the cross-member editor, we can assign every structural element that we want to be linked or referenced to the axis of the bridge. Okay, after this further explanation, I would simply deselect the structural point by clicking the escape button on my keyboard, and basically we can leave the cross-member editor now by clicking on the close button. And if we look our structure now, we can see that the support conditions are defined in the middle support, at the end support, and at the beginning support. It is always useful to save your project, so I will click on the save, and now the project has been saved. Before we export the model, I would like to show you a very easy way to verify the definition of the model here in SOFI Plus. If you simply click together the middle mouse button and the shift button from your keyboard, then you will be able to rotate your model and you will see the contour of the cross-section. This will enable you to find the problems at the definition of the cross-sections if there is any. For example, in our example file, you can see that the middle pier cross-section is rotated with 90 degrees. This is not how we want the pier to be aligned. So we need to rotate the cross-section with 90 degrees somehow. And this is exactly what we are going to do. If I zoom into the structural line and select it with a double click, then we can see the local coordinate system of this structural line as well. The local x-axis of a structural line points always from the beginning point to the end point. And the local y and z axis are perpendicular to this direction. However, in our case, we should rotate our cross-section about the local x-axis. We can do that easily if I click on the escape button and terminate the command. Then we need to go and find the Find and Align chapter. Here we need to select the Align Elements command and select the structural line and hit enter. Here as the second entry you will find Rx rotate around local x-axis, so I will simply click on it and I will enter 90 degrees and hit enter on my keyboard. Now I will click on the escape button to terminate the command 2 times, and then I will double click again on the structural line to double check the local coordinate systems. Now what I can see is really that the local y and local z axis are rotated. Okay, now I will terminate the command by simply clicking on the escape button, and I will double check my system again by clicking on the shift and the middle mouse button, and now we can see that the pier in the middle is oriented in the correct way now. Before I export the model, I would like to give some additional information regarding the model creation. One of these is the following. If you select, for example, this structural line, you will see again this axis symbol, which means that this structural line is linked to the placement number 3 on the axis called axis. What I would like to explain about this is that let's suppose that, for example, you create a structural line or any kind of structural entity, but you forgot to define it within the cross-member editor. Fortunately, you don't need to worry about this because you can also link this structural entity later on to any of the placements. Let me show you this now. So I will just simply create a new structural line anywhere in the graphical user interface, again as a cross section, and I will just simply come here and draw it like this. I will terminate the command by clicking on the escape button 2 times. And now if I select this structural line, as you can see, there is no axis icon next to it, so it is not assigned to any placements yet. But now I can assign it to the placement number 3. We can find this icon here, link an object to a placement. If I click on it, then the help menu says to me, please select an object to link to the placement. So I will select this structural line, and then now I need to add enter. And now I need to select the placement I would like to assign to. So I will select placement number 3 and hit the enter. And then I clicked on the escape button to terminate the command. If now I select the structural line, I will see the small axis icon next to it. So it means that now it is assigned to the placement number 3. Let's see how it works if I change, for example, the geometry of the axis. As you can see, my newly created structural line is located here somewhere. Now let's go back to the system definition, especially into the axis definition, and change the horizontal alignment. Instead of a straight line, let's add an arc, or let's change this to an arc with a radius of 100 meters, and then click OK. As you can see, now my structure has been changed automatically and adopted to the changed axis. Also, we can see that the position of this newly created structural line has been adopted to the changed axis because we linked it to placement number 3. Okay, this was something that I wanted to add as additional information, but I'm going to set back the geometry of the axis to its original position, and I will delete the newly created structural element by select it and simply click on the delete button, and I will go back to the isometric view. And there is also something that I would like to point out here. Namely, that you can verify if a structural line is assigned to the axis if you select it and have a closer look at the end object snap point of it. You will find a small blue triangle at the end as an object snap point, whereas if I select an other structural line, you can see that the end object snap point is marked with a blue square. So if a structural line is assigned to the axis, then the object snap turns to a small blue triangle. And if a structural line is just simply assigned to a placement or not assigned to the axis or to the placement at all, the end object snap point will be a small blue square. Okay, now as I mentioned all the additional information I wanted to, let us quickly export the model and have a look at the exported structure. But before we do that, do not forget to save the model, so I will push the Ctrl and S keyboards on my keyboard to save the model. I will simply click on the export button and accept the default settings. I clicked on OK, and now we can have a look at our structure in the system visualization. If I click on it, the system visualization will be open up, and we can have a closer look at the structure, rotate it if we want to, but for me it seems everything is fine. If you find the support symbol and the spring symbol a little bit too big, then you can simply change the size of these symbols with the support and hinges slider here. And it seems to me, as I said, that the system is well defined. Okay, that concludes this chapter, and I will show you some very special things with the help of the secondary axis in the next chapter. So in this chapter I'm going to show you the possibility to use secondary axis to create certain structured elements within SOFI Plus. Before I jump into this chapter, I would like to ask you to just simply lean back and watch what I'm doing. You do not need to reproduce what I'm doing. This is just a representation. What are the capabilities of the secondary axis? And I didn't want it to mess up the original model, so I have copied my original model into a separate new folder, and I am doing the changes in this copied model now. So please do not make the following changes in your original model. The command to create secondary axis can be found on the System tab, Axis, and as the last entry you can see secondary axis. Contrary what you think, you need to right-click on the secondary axis, and then you can create a secondary axis with an offset. But there is also an opportunity to create a secondary axis from an already created 3D AutoCAD polyline, for example. For demonstration purposes, I'm going to use the Create Secondary Axis with Offset. If you click on it, you will find this dialog box in front of you. First, here you can select a name. So it means that, for example, the name of the secondary axis will be the following. The beginning of the name will be inherited from the main axis. In this case, it's going to be axis. Then comes a dot sign, and then comes the name that you enter here. A positive value means an offset to the right side, whereas a negative -5 meter, for example, means there will be a new secondary axis created on the left side of the main axis, as you can see. Okay, now let's make another secondary axis with an offset. In this case, the name will be B, and the offset will be 5 meter to the right side of the main axis. Let's have a look at it. Yes, it has been created. Now on these secondary axes, it is also possible to define structural elements such as structural points, lines, and areas. Since we already know how to define structural lines, I think it is more interesting how to define structural areas. On the Structural Elements tab, we can find the definition for the structural areas. If you click on it, a new dialog box will open up for you. And again, I try to go through the main tabs of this dialog box. On the very first tab, you can set a number for the structural area, a group number as well, and you can choose the materials for the structural area itself and the reinforcement in the structural area. On the Meshing tab, you can select whether or not you want to control the meshing. Maybe you want a regular grid, or you want to mesh the element that you are creating as a single element. Also, you can control the density or the overall density of the mesh in the structure area. Similarly, you can also control the density at the corner points of the structural area. If you go to the Support or Bedding tab, You can add support conditions to the newly defined structure area in the form of fixed supports, as we saw at the structural line and at the structural point. However, you can also define bedding to the structure area. Finally, you can control the geometry of the structural area on the Geometry tab. By default, the alignment of the newly created structural area will be centric. Now we do not need to set anything because it's just a demonstration from our side. What I would like to show you is how to create structure areas. If we go to the top view, for example, here, and turn off the snap, then it is easier to define the structure area. Right now, by default, I'm in the polygonal mode. So it means whenever I click, the structure area corner point will be added. And if I click with my right mouse button, I just simply choose the enter and the structure area will be closed and created. However, I'm still in the definition mode. So I can continue defining new structure areas, and this time I will choose the segment on axis. Now I just need to pick a segment on an axis. I will choose the newly created secondary axis, and then I need to pick an opposite segment on the axis. I will choose the main axis, and now the software asks me whether or not I would like to create the structure area between all the placements or use the segment closest to the pick point. I will choose between all placements, and the structure areas have been created. Similarly, I will define new structure areas on the other half or on the other side of my structural line. So I will simply now choose the axis, the main axis first, and then the secondary axis. And again, the same question. I will choose between all the placements, and the newly created structural areas can now be seen on my screen. I will terminate the command by clicking on the escape button on my keyboard 2 times. If we turn to the isometric view and have a look at the structure, maybe we can use again the keyboard combination with the middle mouse button. So I will click the shift button on my keyboard and the middle mouse button on my mouse. And as I rotate the model, you can see that the structure areas have really been created. I will try to zoom in a little bit more and there redo the whole thing. And now you can see it much better. If we zoom in more, you can see that the center line of the structural areas are in the plane of the structural line. We can change the orientation and the position of the structural areas reference to their reference plane as follows. I will go back to the Structure Elements tab and choose the Edit the Structure Areas command. Click on it, and now I need to select the structure area elements. I will go to the top view and simply select the whole structure, and I can be sure that only the structure areas will be selected. And here you can see that first of all, 2 new tabs were added, the Edges and the Loads tab. And second, that the element alignment can be changed to positive local Z and negative local Z. If I set it to negative local Z and click on the Apply and OK button, now we can have a look at what has changed in my model. I will view the isometric view again, and now if I turned on the visualization of the cross sections, now you can see that the structure area element is positioned to the negative local Z direction, and now it is on the top of the cross section. This is reasonable because, as you can see, the local coordinate system of the structure area, you can see that the positive local z points downwards. So if I set the alignment of the structure area to be equal with negative z alignment, then the thickness of the structure area will be applied into the negative local z direction. And that is why we can see the structure areas on top of the cross-section. Another interesting possibility I would like to show you is how to control the thickness of the structure area edges. So here I will deselect the structure area and then go to the top view. And now I will go to the modification of the structure area. And in the dialog box, first you need to set the thickness of the structure areas to be equal with 0 mm and click OK. Then you need to go back to the Structure Elements tab and choose the command which says modify the properties of the border lines between two structure areas. I will click on it and first choose the bottommost edges of the structural lines, right-click with my mouse, and a new dialog box will appear. In this dialog box, for the thickness, I'm going to enter 50 mm and then I will click OK. I will redo the whole procedure and now I will select the top edge of my elements and I will set the thickness to be equal with 200 mm and then I will click OK. If now we are going back to the isometric view, hopefully we will see the change in the thickness of the structure areas. And yes, you can see in the middle over the structural line, the thickness of the structure areas is 200 mm, whereas on the outer edge it is only 50 mm. Okay, now let's try to export this system. And I will click on the OK. And then I will go and open up the system visualization to see it better. Now it's opening. And if I rotate my model and zoom in a little bit, really I can see that on the left side the constant 200 mm thickness for the structure areas is visualized, but on the right side the thickness of the structure areas is decreasing and reaches the 50 mm as I set in SOFI Plus. Okay, now let's go back to SOFI Plus and change the axis alignment to see how the structure behaves. So I will simply go back to the System tab and go to the Horizontal Alignment command and change the straight line kind to arc, the length equal with 70 meter and the radius will be 100 meter and then click OK. And as you can see right away, the whole structure changed and follows the changed axis, which is quite nice. Also, if I go back to the horizontal alignment, no, instead that the placements, and then select all the placements, for example, and then set a rotation about the local z-axis to be equal with 10 degrees and click OK and go back to the top view. Now we can see that our structure is really skewed. All the placements are skewed by 10 degrees. So this is the beauty of the CABD technology. As soon as you change the axis, the main axis of the bridge, the secondary axis will also change on the right and on the left side as well, and your structure will be updated accordingly so you can work on the changed geometry. Okay, so basically that concludes the presentations that I want to make about the secondary axis, and we are going to continue with the definition of the actions and the loads in the next chapter. For that, I'm going to use the original model because, as I mentioned, I have copied the original model into a new folder, and I presented what I wanted about the secondary axis because I didn't want it to mess up the original model. But now I will go back to the original model and continue with the actions and load definitions in it.